is it? Okay, so while I'm setting up the lecture here, so any question regarding the project or the homework? So speaking of homework, for some reason this doesn't work. Well. Okay. Anyway, I will speak louder then. Yes. So speaking of homework, I just want to remind you, we do have written assignment homework, but you don't have to turn them in. What happens on the due date, or short after the due date, I will release a solution to the homework. And I will also release a quiz after a few days after I release the homework solution, so that you have time to go over the homework solutions. And the idea is that you can kind of control your own pace, and you don't have to. If you haven't finished, working on your written assignment, you don't have to actually look at the solution right away. I would not recommend you doing that. I would recommend you looking at the solution only after you have made an attempt in trying to solve the homework problems. Okay. And any, that's about homework. Any question regarding the project 1 assignment? Yes, go ahead.
Do we need to turn in a written portion?
Say again.
Do we have to turn in a written portion?
Yes, you have to turn in you are saying the report for the project?
Yeah.
Yes, that's 15%.
Okay. So
if I remember correctly. I mean, for different projects, this will be, for different labs, the percentage of the weight for the written report will vary a little bit. I believe for project 1, that's 15%.
do we put that in just
You just add it to the repository.
Okay.
Yeah, and commit that with your submission. Even if, the written report, that's an excellent question, by the way. So even if you code, pass all the system tests and unit tests, you are still required to submit a written report on, your design and your implementation, right? So that's really for the TAs to understand your implementation better, even if your code runs smoothly and all that. Okay, so that is still required. But it doesn't have to be an extensive report. As I mentioned in the assignment itself, some fairly high-level discussion is good enough, as long as you have clearly highlight the ideas and the design principles you have adopted in your implementation. That's good enough. I'm not asking you to submit a detailed, documentation of your code. That's not required. Okay. All right. With that being said, let's get to today's lecture.
Yeah, neither do I.
Why is it so slow? As far as I know, last week everything was working just fine. I don't know
Yeah.
why they did this and suddenly I cannot do anything. This is ridiculous.
Are you trying to get a Canvas?
Yeah, I'm trying to get.
Utah.instructure.com is the. You got an extra U in there.
Huh?
You got it's instructor. That.
Just Google it.
There you go.
Cameras might be down. Okay, alright, so the last thing is maybe go through the hard box. Let me make sure this is what I want. Okay. Okay, so let's recap where we stopped last time. We stopped at the discussion of buffer manager, right? So to give you a quick recap, what we said is that you have data in a typical database system. Your database is likely that the data from your database, will be the size of the data in your database will be larger than the capacity of your RAM, of your memory. But CPU, your processor, is only able to operate over data in memory. In fact, it can only operate data in cache. But we kind of, as I explained in last lecture, we kind of hide that level of abstraction, right? Data transfer between memory and cache for the time, right? So we assume, CPU operate over data in quote unquote in memory directly. So if we assume that we hide that level of data transfer, right? So you need to do some kind of data transfer between memory and hard drive. Your hard drive. Your hard drive being either a magnetic disk or a solid state drive, which I will, at the end of this lecture, I will come back and spend a few minutes, to fulfill the promise I made to you of explaining what is the difference between solid state drive and magnetic drive, right? For the time being, we just assume they're the hard drive, either it is a magnetic drive or a solid state drive, that you need to do data transfer from, right, into your memory. For that purpose, database system introduced something called buffer manager, which is something you are working on in your lab 1, as part of your lab 1. So the abstraction of this buffer space is as follows, right? You have a collection of what we call buffer frames. Each frame is of a fixed size. Typically, they are configured to be of your page size or your block size. Page and block, as I mentioned multiple times, in this class, page and block, they refer to the same thing, right? To the same thing. It's basically, if you talk about a hard drive, it's essentially a consecutive set of sectors, right? For example, 8 sectors give you a page of 4 kilobytes if each sector is 512 bytes. Sometimes in modern database system, page size is typically either 8 kilobytes or 16 kilobytes. There is a trade-off, right? You may wonder, is this a magic number, or there is some kind of trade-off when I set a particular page size? Yes, there is, which we will talk about that later on. Okay. For now, let's just assume this is a constant that some database developer has configured system to use, right? 4 kilobytes, 8 kilobytes, or 16 kilobytes. So each of these buffer frame is nothing else but that page size of memory space. That page size of memory space. So in other words, this is, for example, 8 kilobytes memory space. This is another 8 kilobytes memory space, and so on and so forth. Okay, and each white frame in our discussion represents an available frame, and each black frame represents a frame that's occupied, that's currently occupied by a page you brought from disk into memory. And everything works just fine until the moment that you have all the frames occupied in your buffer, right? And at this point, if you request a page that's not currently in your buffer, you need to find a space to hold that page. You have to do this because CPU only operates over data in memory. So you have to first bring this page to memory and place that page into your buffer before you can do anything further regarding that page. Okay? So you need to find a place for that page. And this introduces concept of what we call buffer management or buffer replacement. In other words, when we run out of space, what do? And in order to do that, I introduce a particular data structure we will be using to describe the discussion to follow. In particular, each buffer frame will be using this particular data structure. We have a frame number, then we have a page ID, we have pin count, we have a dirty bit. So let me explain each of these fields in details. Frame number is very easy to understand. It's just an identifier to identify a particular frame in your buffer. 1, 2, 3, 4. It's just some sequence of unique identifiers you set up to distinguish between different frames you have in your buffer. So that's very easy. Page ID denotes the current page ID, the ID of the current page, if there's any that is currently occupying this current frame, this particular frame. Okay? So page ID may be a null value if the current frame is actually available, it's holding no page from disk. But otherwise, if it is holding a page, then page ID is set to the ID identifier of that particular page. Each page, later on in our discussion, I will discuss this in further detail, but for now, just take this as granted that each page in your system, in your database system, is assigned a unique identifier. And that's essentially what a page ID is. Pin count deserves some discussion, right? First of all, why is it called pin count? The reason is so if I get a page, suppose I have this page. I need to use this. I need to find a page. Let's use this page. Suppose this is a page I brought from disk to memory. That's my memory, that's my disk. And I bring it to memory. If I do nothing, what happens? If I let it go, it will drop. Right? So what do? You use the pin to pin it. So it stays in your buffer. That's what pin count does. You may wonder, if that's the case, shouldn't that be a Boolean value, pin or not pinned? Well, the reason is you may have multiple different processes or threads from the higher layer that are currently using this page. Right? And what happened is, okay, suppose I have two processes currently are using this page. The first process was the first one that requested this page and brought it from disk to, somebody has to brought this page from disk to memory. Suppose that's the first process, I pin it. and before I finish using this page, another process comes by and asks for the same page. At this point, for the second process, you don't have to go all the way to the disk to request this page, but rather you can just use the cache version of this page in the buffer, but you declare to all the others that you are still using this page. So you pin it again. So the pin count by now is 2. The pin count, if you understand what I'm saying so far, what that means is if somebody pin a page on a board or something, what does it tell you? It tells you this is useful. Don't take it away. Right? And that's why they pin it in the first place. So if pin count is not 0, that indicates somebody is actively using this page. Don't do nothing about this page. Once the process has finished using this page, remember, they don't have to be in order, meaning the second process could be actually the first one finished using the page, even though it was the second one come to ask for this page. It will decrement the pin count by 1, so it will go back to 1. And then sometime later, the first process also finished using this page, decrement the pin count again. By this point, pin count becomes 0. That make sense? This is where buffer is different from physical world. In a physical world, if you remove all the pins, page will drop automatically. In the buffer, imagine there is a loose glue force somewhere. So pin count goes to 0, the page doesn't go away automatically. It will stay around in your buffer unless somebody forces this page to be kicked out. You may wonder why is that? Why don't you just kick the page out? Well, the hope is that you want to leverage this concept called locality. If some processes have been using this page, then chances are another process may come back and ask for the same page. So if I let this page stick around for a little bit, maybe its pin count will go back to 1 or 2. So don't kick this out unless it's absolutely necessary. When it is absolutely necessary, when you do need to create space for new pages, when you run out of frames. That make sense? So if you understand what I'm saying so far, what the pin count does is to tell you whether a page is a candidate for replacement or not. If pin count is not equal to 0, that means you absolutely cannot remove this page because somebody is actually still actively using this page. Kind of like somebody is holding quote unquote a lock on this page. But if pin count is decremented back to 0, what that means is all the processes who were using this page are done with this page. Now you can safely remove this page from buffer and make room for other subsequent page requests. Okay, so that's the purpose of pin count. And lastly, what dirty means. Okay,
Just double check. So you said when the pin count goes to 0, it doesn't automatically get removed.
It doesn't automatically get removed. Yes, but it becomes immediately it becomes a candidate.
It's tagged.
Yeah, it's tagged to be replaced by some later request if needed. Okay. Now, the last bit, the dirty bit, is the Boolean value to indicate whether the page has been modified or not since the last time it was brought into the buffer. To understand this, I will draw this picture here. So suppose that's the page, and this is the buffer. And suppose this is page 10. So somebody pin page 10. When this request comes in, I will go fetch this page, bring this to the buffer, and I will label it page 10. And at this point, my pin count is 1. My pin count is 1. However, the content of this page is identical to the content of that page in disk. And imagine if I finish using this page and I decrement the pin count back to 0, and suppose all the other are occupied as well, and I request page 12, and there's no space, I decide to take this one out. You can, because pin count is 0, you can definitely do that. In this particular scenario, all you need to do is to safely discard this page. In other words, you can simply override page 12 on the content of page 10 in memory. You don't have to do anything regarding the disk copy of this page because nothing has changed. But imagine yet another scenario where I brought this page into the buffer, and this is 10, pin count is 1, and initially the content of this is identical to that, but this process has done some update to this page. Suppose I have modified this part to be green. Now, if I request page 12 subsequently, and of course pin count back to 0, I finish updating this page, pin count back to 0. Now, you cannot simply throw away this page and write page 12 over page 10. Right? Because if you were to do that, whoever did the update lost his or her change forever. Right? So what you have to do is to write this back to disk so that the content of the page 10 on disk is now synchronized with the copy of this page in buffer. And how do I know? I being the buffer manager, how do I know whether the content of page has changed or not? I leverage that dirty bit. Initially it's set to 0, and if somebody has updated the content of this page, since it was first brought into the buffer, I will set that dirty bit to 1. And a key observation is that no matter how many times updates have been made to this page, since it was brought into memory, I only need to set the dirty bit once to indicate whether it's been updated or not. I don't have to keep track how many times it has been updated. Because at the end of the day, I only need to write the latest version of this page back to disk. So far so good? Any questions so far?
So if that original program process that actually updated it, if it, let's say the user saves the word, does that change the dirty bit back to 0?
Okay, excellent question. Save the work, right? That's the key word, right? If the user had saved the work, does it change the bit back to 0? You are kind of actually bringing up a concept that will occur much later in this course, which is in database, in buffer management, what you're saying is this force policy, which is whenever I finish my process, meaning I save my work, I force the buffer manager to write any update back to disk right away. Right away. It's like you use Microsoft Office, you don't trust the autosave function, you save every minute, every 5 minutes, you physically click that save button. That's like what you're doing, right? Of course you can do that. You can design a database system works just like that. Meaning whenever a process has finished using the page and document the pin count back to 0, and if the page is dirty, I force you to write this back to disk. But think twice whether this is really an efficient design. Not really, right? Imagine one process has updated this page, document the pin count. If I use the force policy, I write this change back to disk right away. Later on, another process is also using the page and finish updating the page. You write again. So if this page has undergone 10 or 20 different updates, you need to write the content of this page 10 or 20 times back to disk. Does that make sense? Versus the lazy approach. The lazy approach is, as long as I have space in the buffer, all the changes are actually just made to the copy of this page in the buffer. You don't force writing this back right away. Only when later on somebody decides to replace this page, that's the only critical point I absolutely need to write this back to disk. So during this period of time, if the content of the page in buffer has been updated 20 or 30 or 100 times, at the end of the day, I only need to write the latest version back to disk. I only need to do one write to disk instead of doing 20, 30, or 100 times the write. So your efficiency is way better. Does that make sense? Did I answer your question? But your question did bring up yet another interesting challenge, which is fine, you can do the lazy approach, but there are no free lunch, right? This is This is the volatile. What happens if, you know, you're saying, okay, I'm not gonna do the force update. I'm smart. I'm smart and lazy. I will wait until absolutely last minute to write this back to this when necessary. Somebody kick me out. I write, no matter I accumulate all the updates so far. So this is update 1, update 2, update 3, and I don't have to write 3 times. I only wait until last minute when I have to kick this page out. I write all of them at once back to disk. Perfect, no problem. So this is still like this. When this has undergone 3 updates already. You know what? Your server happened to be in Key West, right? And before you decided to write it back, Hurricane Irma came along. You know? Of course, it's as always, right? News media make big fuss about this, like, oh, it's gonna be end of the world, and it happened. The reality is always much better than what they forecast. But still, yes, still, the damage was enough to bring your server down. The power is lost, and you know what? You know nothing about what happened. And you were trying to be lazy, but guess what? Now you have more work to do because you have to somehow recover what you have done before. So how do you address this dilemma, right? So this particular discussion, unfortunately, we are way early in discussing this. This requires a lot of machinery to get this right. So we will talk about this towards the second part of this course. For now, imagine there's some magical process that can somehow remember the history for you. If Hurricane Irma comes along, it can magically restore everything to be right before Hurricane Irma, without paying much cost. Of course, there's a cost associated with that. If doing that is very costly, you know, I'm better off doing the force policy. So far so good? All right. And that's probably, you know, you notice from your lab 1 implementation, for many methods you are implementing, there is a parameter called transaction ID or something. That you're not using that. That transaction ID is a placeholder for that magical process to do the rescue work for you if things really bad are going to happen to your system. Okay? Later on we will have a lab for that particular purpose, for transaction. Okay? All right? So this basically just repeats the discussion I have, so I will skip all of them. Now, the only thing left for buffer management is really, okay, now fine, I understand all this discussion, and the only thing that's not clear that we haven't touched on is, you know, if my buffer is full, and I have a new page to go in, which one should I replace? Which one should I replace? Of course, one thing that's clear, you should only replace those with pin count equal to 0. I'll bring another color. So given the setup like this, you should only consider these guys for replacement, but not these 3 frames, for example. Because if pin count is not 0, it means that it's being actively used still. You cannot replace that. But even you have that, you still have a choice to make, right? You have multiple pages with pin count equal to 0. What do you do? Which one you replace? Of course, you can make the decision randomly. Randomly pick one and replace that. But you want to do better. Typically, random batting is not the most effective strategy, right? You want to choose one that makes sense, right? It's like if you play, I hate to use this example. I know we're in Utah, but there are no other. When talking about randomization and probability, there are no example better than gambling, right? So bear me with that if you know about gambling. So if you go to Vegas and you play blackjack, 21 points, right? You won't, I bet nobody will use the random strategy, right? Whether to ask for another card or not, you won't make that decision randomly, right? If you have, if you have 20 points already, I bet you won't ask for another card, right? Unless you are sure you've been remembering all the cards that the only card left is the ace card, right? Then you go for it. Otherwise you won't, right? So you won't use the random strategy. You want to use some strategy that's better. So what kind of strategy we should be using here? It's kind of similar to gambling in some sense, right? You are trying to predict what the future looks like. Let me give you an example, right? Let's say you use the most common policy called IRU, which stands for least recently used page. Meaning, among the pages with pin count equal to 0, which one to replace? Well, you replace the one that was least recently used. Meaning, the last access to that frame was is the furthest one back in history. That's least recently used. Does that make sense? What's the intuition? The intuition is, I'm gonna replace the page that hasn't been accessed for a long time. So the fact that it hasn't been used for a long time indicates that the chance for somebody to come back and ask for that page is low. I'm leveraging this particular intuition. So you do that. And let me use an example to demonstrate this. Suppose this is my hard drive, and I have six pages here, and I have a buffer. Unfortunately, it's only able to hold 5 pages. Okay? I'm only able to hold 5 pages. Now, my request sequence is 1, 2, 3, 4, 5, 6. I tell you that's my request sequence so far. And what happens? You bring 1 to the first frame, and the pin count was 1, then immediately back to 0. Suppose that I'm doing a read-only access. So the pin count was set to 1, and immediately was decremented back to 0. 2, I'm going to omit the pin count. They all are the same, right? So pin count 1 become 1, and back to 0 immediately. So far that's been the request sequence. And if you are going to use, suppose you are using RRU, and now you request 6, which one you are going to replace? 1. Right, this is the least recently used. You're predicting, you're betting on the future. You're betting on the future at this point, right? Imagine what happens next. A lot of things could happen next. Right? I could request, for example, 1. And if that's the case, if you keep using RRU, what happens? You realize you made the worst decision, right? You can, right? Out of the 5 choices, any other one you choose, you will have a buffer hit. But the one you replace is exactly the one to be requested next. So you have to go to disk again and get this page in. Now you replace 2 by least recent use policy. Now observing what you do, suppose this is the game, I observe what you do, then I request 2. You're like, what the heck, you keep doing this, right? So it's the worst strategy ever. But okay, let's play the game again. You say, okay, once you observe what I'm doing, you say, wait a minute, I'm gonna replay this game. I'm not going to use RRU. Okay, this stays the same. When you request 6, I know I predict you're gonna request 1, 2, 3, 4, right? So what I'm gonna do is I'm gonna replace 5. Right? But I can change my strategy too. I will observe what you're doing. If you replace 5, what you're doing is you're using MRU, most recently used. The intuition is also clear that if something has just been used, recently used, the chance you come back and use the same one is low. It's kind of like if you go to the union, if I know what you had yesterday for lunch, I will predict you will have something else for lunch today. But for this union, it's hard to predict because the food is so bad. My strategy has been either random or stick to one choice, even that one choice is just barely iterable, right? So this union is hard to predict, right? But in a typical union place that offer food, you will go with different choices, right? So you go 6, and you replace 5, and I will request 5. And you say, okay, too bad, I made a wrong decision, so I replace 4. I stick with MRU, I will ask for 4. So you see, no matter what you do, so I don't think I need to continue this game further, right? You can kind of tell what's going on here. What's going on here is no matter what you do, if you allow the other side to be kind of adversary and observe what you do, knowing your strategy, this game is hopeless. This game is hopeless. Does that make sense? So this introduced this particular idea called online algorithms. Online algorithms. Online algorithms is to be compared against offline algorithms. Most, if not all, algorithms you guys have written so far are what we call offline algorithms. An offline algorithm is an algorithm that's designed when you are given all the input at once. You are given all the input at once. But look at this particular problem we were just trying to solve. You were not given the input at once. You were given input one at a time. You have to take an action before seeing the next input. You have to take another action to see the next input, so on and so forth. And before you take an action, you do not know what the future inputs look like. Pretty much like buying stock. Luckily we have this online algorithm and things are not all offline in nature, because if that's the case, everybody become millionaire. Right? Because if stock market is to play off one day, then let people to buy, historical transactions, this game is not you cannot play this game, right? When everybody become millionaire, everybody is equally poor. I don't know whether you realize that or not, right? So don't buy this bait. Oh, I'm gonna give you this and that. If everybody was given the same thing, everybody is equally poor at that point. That means nothing at that point. So online algorithm play a really, really important role in our society, right? Stock and many, many other things. So the question is, how do you design a good online algorithm when you do not know the future? And that's question number 1. Question number 2, how do you quantify how well a job you are doing? Like, for example, how do I compare IRU and MRU? You may argue, wait a minute, this comparison is making no sense. You just said, I just said, Fifi just said, no matter whether you're using IRU or MRU, there is an equally bad case that happened to them. How do you compare the two when they are equally bad? Well, the key insight is they are equally bad if you allow the other party to be adversary in nature, meaning change the input dynamically in an online fashion by observing what you do. Typically, that's not the case. You do not have this supernatural power that controls the input. Does that make sense? So, to quantify the performance of different online algorithms, people introduce competitive ratio. To understand this, so what I'm gonna show you is this definition of competitive ratio. Then I will analyze the competitive ratio of MRU and RRU and conclude the discussion by saying which one is better, which one is not. Okay? So the idea is false. So imagine I have my particular input. This input is from an input space, calligraphic I. This denotes the set of all possible inputs. So, for example, in our example, if I tell you I have 10 pages on my disk, if I have 10 pages with page ID 1 to 10, what is the possible input? What is the possible input? Well, I'm gonna, for example, I also tell you I have a request sequence of, let's say, 1,000 requests. what is a possible input? Well, for a solid example, this is a possible input. Right? This is a particular I. This is a particular I. What's all the set of all possible inputs? Well, that's a lot of them. Can someone tell me what's the size of this in this case?
10,000?
Huh?
Is it 10,000?
10,000. Okay, answer 1 is 10,000. Why that? Are you saying 10 times 1,000?
Yeah. Because there's 1,000 slots and you can choose one of the 10 pages for each of the slots.
Okay, so then in that case, if that's what you're saying, it's actually 10 to the power of 1,000.
Yes.
Because each position has 10 choices, right?
Yes.
Each position has 10 choices. For 2 positions, you already have 100 choices.
That's
For
right.
3 positions, you already have 1,000 choices. So for 10,000, for 1,000 position, it's not this, it's 10 to the power of 1,000.
That's right.
Much, much larger than 10,000, right? 10 to the power of 1,000. I mean, if you compare 10 to the power of 1,000 versus 10,000, it's kind of like comparing the universe against probably this chalk. That's the size comparison of the two. Okay? So it's much, much larger. Okay? But you understand what I'm saying, right? You may wonder, what's the input that's not from this input space? Well, imagine if I change this to, then this is no longer a valid input because you are requesting a page that's not even from my page ID space. That's invalid. Does that make sense? Yes or no? Yes. Okay. All right. If you understand the discussion so far, okay, I'm gonna show you the definition of kinetic ratio. Okay. I is one particular input from that input space. In our example, 1 out of 10 to the power 1,000 choices. And when you are designing your algorithm, you don't know which I I'm using. You don't know which particular I I'm using, which input I'm using. But suppose once you fix I, but still you don't know which I have fixed up, right? You don't know which choice I have made. But I tell you, I have chosen 1 out of these 10 to the power 1,000 choices, and I'm not going to change it, no matter what you do. That's my input. Now, design your game and let's play this game. But I don't tell you the input ahead of time. But I fix my input. I'm not going to change the input. You have to trust me. It's an honor system. We are all gentlemen, and you have to take my word for it. I take my input and I fix it. I just don't reveal the input to you. You follow me? Now, given this I, there must be at end a buffer size k, meaning k frames of your buffer. Your buffer has k frames. There must be a optimal algorithm. On this input I and this k. If you gave this algorithm the entire sequence I and the size of buffer, I can design an optimal algorithm to minimize the number of buffer replacement I have to do. And this is what we call an optimal offline algorithm. Why is that? Because you are given this algorithm the entire input I, meaning the input was given ahead of time. So that's an offline algorithm. Does that make sense? Yes or no? Okay, so far so good. Now, of course, for each different input I, the behavior of this offline optimal algorithm will be different. I will adjust my algorithm based on what this input looks like. But no matter what, there is an optimal cost for a given input once it's fixed. And if you give this entire input at once, I can design an algorithm that's optimal. with respect to that particular input to minimize the cost. Where the cost represents the number of buffer replacement you have to do. Number of buffer replacement you have to do. Do you follow me? So far so good? Or no?
Can you repeat this last question?
The cost is the number of buffer replacement you can do. And given an input, I can design an optimal algorithm. The algorithm might be really complicated, whatever, I don't really care. But there is such an algorithm, for sure, that minimizes the number of buffer replacement once the input is fixed. But I have to know the entire input ahead of time, so it's an offline algorithm. Now, design your online algorithm. Now, your online algorithm, let me denote A as the class of online algorithms that you can design. For example, RRU, MRU, so on, or random, right? Whatever. But it must be a valid online algorithm. For example, one that replaces only a page with pin count equal to 0. An algorithm that replaces a frame with pin count not equal to 0 doesn't belong to this class because it's not a valid online algorithm in our problem set. Now, given this class, this is a class of valid algorithms online, meaning you do not know the input I ahead of time. And A is one particular algorithm from this. For example, LRU. Okay? This A on this input I and this buffer size K must have a cost. But when I write like this, what that means is A doesn't say the entire I input at once. A says the input one at a time. And perform an action, then you are given the next input. But the key to this game is that I was fixed before the game starts. And I compare that against the cost of this offline optimal on this particular I, on this K. The only difference between the two is that in this case, I was given one at a time, and you have to perform action. Here, I was given, the entire sequence was given to this algorithm, and the algorithm design is action, then play the game. One observation that's clear, this cost, of course, must be greater than or equal to this. You cannot do better than the offline optimal. Right? So this ratio must be greater or equal than 1, in other words. And this ratio, of course, depending on K, right? Why? For example, in a straight case, let's say K is greater than 10 in our example, then no matter what you do for your online algorithm and the offline optimal, the ratio is 1 because there will be no buffer replacement. There are only 10 pages. You request 10,000, 1,000, whatever, everything gonna fit in memory, there will be no buffer replacement whatsoever. So the ratio will always be 1. So obviously this depends on the value of K. K is important. You follow me? So it's not as trivial as it might look. It's actually very complicated. This is a very complicated game, which it should be. Otherwise, everybody can make money from stock market. Because this is exactly stock market. Like you're betting, for example, a particular stock price will go up or go down. And to be more competitive, you're betting not only one particular stock will go up or go down, you're betting how much it will go up and how much it will go down, given thousands of stocks to choose from. And this is what we call the competitive ratio. And of course, for different I, this is one ratio, right? For different I, this ratio is different. Now, to quantify the performance of an online algorithm, we look for the worst case scenario. When do you perform the worst compared to the offline optimal? So among all possible input I, here I ignore that value K, right? I assume that the buffer size K, but I ignore that from my formulation. The rest is exactly the same as what I said on the whiteboard. So for all the input, I do this. For all the input, all the value input, I do this. And I look for the point, meaning the input sequence where this ratio is maximized. This ratio is maximized. And I use that to denote the performance of this online algorithm. In other words, in the worst case scenario, how bad you are compared against an almighty, offline optimal algorithm who knows the future for all possible input sequences. And I use this to compare two online algorithms. In other words, I use this to compare two stock brokers and decide which one I should invest with. Do you follow me?
So,
Okay.
do we need to go through all the different possibilities, like 10 to 1000?
That's another way. If what you're saying is, we can also, of course, compare the two using the expected cost. Meaning, the ratio times the probability of an input sequence. If you're assuming uniform distribution, that simply is the sum of this ratio. Unless there's a skew distribution on your input space. Of course, that's one choice. But in this particular case, think about is your money. If you are an investor who care about integrity and safety for the most part, you will not go with the expected value analysis. You will go with the worst case analysis. In the worst case, how much money am I going to lose? How much profit, in other words, I'm potentially losing here, compared to the optimal dealer who knows the future stock price. Of course, that's not possible, but let's imagine I try to compare against that. That's my potential profit loss. So I'm looking at the worst case scenario. Of course, you can use the value analysis, but in this particular case, people always use, for the most part, people mostly use worst case analysis. Very good question. Okay? So far so good? Of course, computing this is not easy, right? For the simple setup I showed you earlier as an example, with 10 pages, 1,000 requests, the input space is already 10 to the power 1,000. If you want to calculate this literally according to this formula, you have to iterate through each input sequence, which is 10 to the power 1,000 of them, and good luck with that. By the time the universe exploded completely, you probably haven't finished your calculation yet. That's true, right? Because the number of particles in the universe is about 2 to the power 80 something, I believe. And 10 to the power 1,000, I believe, is larger than this. So in order to do this calculation, literally you are counting all the particles in the entire universe, and more than that. I don't know if you can do that. You probably, by the end of your lifetime, you won't be able to count the number of particles on this table, I guess. Physical, in the physical world, the particle, not like particle in the common sense, right? The particles, like atom and molecules in that level. The number of particles on this table probably is in the millions or billions at least, right? So you cannot do this. Are we hopeless? No, we are not. There are smart ways of computing this. Of course, that's beyond this course. If you're interested, Google online algorithms and Google competitive ratio analysis. Okay. And I have a result here. You don't have to understand this. It's just FYI, right? To show you the competitive ratio, for example, of IRU. What's interesting to know, though, the competitive ratio, can someone guess? What's the relationship for the competitive ratio of IRU and MRU? Should be the same. Because they are symmetric, and they should be the same. In the worst case, they compare to the offline optimal, they should be identical. Because the two behave almost in a perfect symmetry, right? It's like two guys to decide if I want to go from here to the opposite direction of Earth. One says, oh, going to the east is better. One says going to the west is better. Guess what? They're equally good. They're going to meet right over there. If they keep the same pace, they end up in the same spot at the same time. exactly the opposite. Of course, you have to assume Earth is the perfect, circular surface, which is Earth is not that way. If you don't know that, the diameter of Earth this way is slightly larger, I would say, than this way. So it's not a perfect circle. All right, that's competitive ratio. And there's another class which, since I'm here, let me talk about this. There's another concept called instance optimal. Instance optimal says it's very, it's almost the same as this analysis, but sometimes I don't want to use offline optimal as my base of comparison. You may argue why. Why don't you compare it to this offline optimal? Because offline optimal denotes what's the best scenario. What can you do? Why don't you compare against that? Well, the reality is oftentimes it's hopeless when you compare, in some scenarios, it's hopeless to compare to the offline optimal. Because offline optimal is simply too optimal. When everybody compare against this guy, in some problems, not in the buffer replacement case, but in some other cases, this ratio will always be infinity, no matter what. Meaning the offline optimal is just too good. There's no way, no chance you can beat this guy. There's no way you can beat this guy. So everyone compared to the offline optimal is infinity, and then make the comparison meaningless, right? So instead of compare against the offline optimal, I compare to the online optimal I star. Online optimal A star on I. So what this means? Remember, there's no single online algorithm that's always optimal. We saw that example from RRU and MRU. It heavily depends on the input sequence. However, given a particular input, there must be one online algorithm that's optimal for that instance of input. I'm not optimal for all input instances. I'm just optimal on that particular input. I could be really, really bad on all the other inputs, but I'm really good on this one input. I'm optimal in this case. So, instance optimal says I'm going to compare the performance of online algorithm against the optimal online algorithm on that particular input, which change from input to input. And I quantify the difference of that. And that's another ratio. And you take the max ratio of that. That's called the instance optimal competitive ratio. And that's another machinery people often use. Does that make sense? Let me give you an example, right? So think about this as stock trading. And the input, let's say I give you an input sequence which consists of only tech stocks. And there's one dealer who knows only tech industry. He or she knows nothing about anything other than tech industry. Like if you ask him whether Mercedes-Benz is better or what's the car that's small enough, not even BMW, like fit just one person, what's the car?
Smart car?
Smart car, whatever. I saw that all over Europe, right? Never see that, seldom see that in the US, right? Like the smart car, right? The really, really small car. If you compare Mercedes-Benz versus this and ask him which is more expensive, no brainer, the answer no brainer, right? But he says, I don't know. So it's such a dealer, right? He or she knows nothing about anything other than tech, and particular IT tech. But if you ask him or her, is Google doing search business or is LinkedIn in search business, he or she can give you a perfect answer. And the input sequence, it consists of only IT stocks. So that's the online optimal dealer I'm talking about. But if I change the input to anything other than only IT tech stocks, that algorithm suddenly becomes so bad. That's an example of instance optimal. Does that make sense? All right. So there's a competitive ratio, which is just FYI. You don't have to understand this, but I'm just showing this for the interest of knowledge, right? But you don't have to understand this analysis. Okay. Now I will skip this discussion DDMS versus file system. Hopefully I will have time to come back to talk about this. Now that concludes the discussion on buffer. Okay, and the key point is to understand how buffer works and the concept of online algorithm and compatible ratio. And hopefully you will be using those concepts later on in the design of your online algorithm in your work with Google. I mean, online algorithm is everywhere, right? Like for example, Google has to use online algorithm to predict, which page I should crawl first. They have a crawler going all over the internet. Of course, one strategy is to design a random crawler. Given any page on the internet, there's an equal probability my crawler will crawl that page today. But I have limited resources. I cannot crawl all the pages on the internet. So from Google's point of view, I have to somehow predict which page will be more popular in the next few days. So I will have a higher probability to crawl that page. And that's predicting the future. You never know which page is going to be popular in the next few days. If there's no hurricane, the Wikipedia page on hurricane probably is a very unpopular page. But suddenly, if there's a hurricane coming over, I'm sure that page has been Googled millions, if not billions of times. But it's very quick. After the hurricane is over, nobody cares about that page anymore. I still care because I'm curious. I'm curious of why all the time. Right? But most people probably don't care about how hurricane was formed and all that stuff. Right? Does that make sense? So online algorithm is everywhere. Okay? The fundamental reason, if you think about why people need online algorithm, is you have limited resources and you cannot predict future. Combine the two. Because if you have unlimited resources, you don't care about online algorithm anyway. Like you have unlimited supply of money. You ask me how to invest on stock. You know what? Buy everything. Unlimited amount of money. The up and down make no difference on your money. It's plus infinity. Does that make sense? Unlimited resource means you don't care about your strategy anymore. When you have limited, like if I have like billions and billions of dollars, you ask me where to buy in Salt Lake, buy all the houses, I don't care. But if I only have 500K, well, you know what? I do care where I buy. Right? So it's a limited resources combined with predicting the future. Right? Buying where in Salt Lake City, you want to buy where the price may go up the most. You want to predict that. Now, change gear a little bit. So now we understand buffer manager. Now let's go down one level to the level of disk. How we manage files and records on disk. This introduced the concept of files of records. So each database is a collection of records, right? So suppose I'm on the Postgres database. I connect to the DVD Windows database. That's part of your homework 1. I show the tables. I select star from actors. So these are the records. Where do all these records go? Well, it goes to a particular thing called file. A file is a collection of records. And the file is an abstraction that needs to be able to support insert, delete, modify of those records, and fetch particular record and scan all records. What I just did is scanning all records in the file, essentially. So you need to support these operations. And to do that, files use a level of redirection. Instead of managing record directly, they manage something called pages, as we mentioned multiple times. So instead of saying, okay, I'm going to manage all the record directly, I'm going to manage instead just a set of pages. And each page, in turn, has a set of records of their own, right? So the question boils down to how do I manage, from the file's point of view, how do I manage a set of pages? And there are two different organizations. This is what we call heap file. Heap file has two organizations. One is like this. I maintain two linked lists of data pages. On the top, this linked list consists of data pages that are full of records, meaning there are no space left on that page to hold any free record. If you try to insert any new record to that page, you will fail because you don't have space. The bottom linked list consists of pages with some free space, meaning I can continue accommodating new records coming into that page. And then I have a header page. The header page is to store some metadata information about the file, like the table name, that this file is responsible to, and how many records, what is the average record size, and so on and so forth, how many data pages I have, like some metadata information about the page, about the file, sorry. And that's one organization. Another organization is to do something like this. The downside of this organization is being a linked list, meaning that it means that to do random access to any given page is potentially expensive because it's a linked list structure. Right? It's a linked list is really designed for sequential access. It's not suitable for or not good for random access, jumping to any page. Right? So using that observation, another design is something like this. I'm not going to organize all my data pages into linked list structure at all. They are just going to be randomly located all over the place in my memory space. And in order to keep track where they are, I'm going to use some pointers to remember where they are. Pretty much like managing objects in your memory space. I view these data pages as objects in memory space and using pointer to keep track where objects are. And these pointers, together with some metadata information that I attach with each pointer, such as the page ID, the number of records in that page, the record size on that page, and so on and so forth, that form what we call a directory entry for that data page. So there's directory entry 1 for data page 1, directory entry 2 for data page 2, and so on and so forth. Then I organize these data entries into pages themselves. This may occupy more than one page if you have many data pages, but even though I have same number of directory entries as I do have, for the number of data pages, this same number of directory entries will occupy much less number of pages compared to the total number of data pages I have. Why is that? Because each directory entry is much smaller in size compared to a page itself. You only have some metadata information. So I have this organization. So if you compare these two approaches, the overhead of the second approach is bigger than the first one because the first one, you have only one extra page than actually needed to store your data. The second one, the directory entries may occupy more than one page, several or tens of pages. So the overhead is a little bit more, but the benefit of having that overhead is now you can do random access to any data page very efficiently. Because you kind of you have a set of pointers to manage these pages. I will skip the discussion on indexes. Let me continue on with the discussion on records. So now we understand how we organize pages. That's pretty much what you're doing in your lab 1. But we're not, lab 1 goes to a finer granularity than just, managing the pages. You have to look into what's inside each page as well. So that's the following discussion is designed for. Okay. Now, in order to understand that, let's first understand how we organize records. Each record has a couple of attributes. Somehow, magically, when you execute this query, the database system is able to do the parsing properly, meaning 1 is for actor ID 1, P envelope is for the first name, and so on and so forth. And it won't show 1 and P as actor ID and envelope as first name. It knows where the boundary lies at. How is that possible? How do you do that? Right? How do you know where the boundaries are between attributes in a given record? That's because we're using this particular approach, right? Depending on whether you're using fixed length or variable length. What's fixed length? Fixed length means each attribute of your record is of fixed length. Let's go back to that example here. If I describe actor ID is an integer. So actor ID is integer. This is not a fixed length record, right? Why? because I have varying character varchar. I explained this to you last time, right? Varchar 45 means that the maximum length is 45, but the actual length for a particular attribute, for the value of that, is the actual number of characters it occupies. Right? Did I have that discussion? I think I did. Right? So if I use char character array, that's fixed length. No matter what's the actual number of characters you name, I'm going to use these many bytes anyway. So this is the variable length. Do I have a fixed length example? Maybe. Yeah, this is a fixed length record. Integer, no matter what the value of the integer is, it's going to be fixed length, like 4 bytes. Timestamp, no matter what the timestamp value is, it's going to be fixed length, maybe, I don't know, 8 bytes. Small int, 2 bytes maybe, so on and so forth. So every single attribute is of fixed length, and if you add up all the attributes, the whole record length is fixed length, no matter what the values that record has. Does that make sense? Okay, so this is fixed length. Now, once you understand that discussion, you can understand what's going on here. If it's a fixed length record, no matter what values each record may have in your instance, all I need to know is the base address of the record, starting address for the record, and the length of each attribute, which is given from the schema specification. And to do the parsing of this record, the values in this record, I simply use the base address as a reference and keep adding the length of each attribute. That way it gives me the boundaries for different attributes. So for fixed length, that's easy. What about variable length? Meaning the actor example. You cannot use fixed length to do this calculation because varchar 45 means that the actual length of this example the length of these two records is different. This part is the same, but for this, I'm using varchar 1, 2, 3, 4, 5, 6, 7, 8. 8 bytes plus typically character string has a trailing ending character, right? So 9 bytes. So on and so forth. This only has 5 bytes. So the length of each record is different. It varies from record to record. You can no longer use this idea to make it work. How do you do it? Well, you have to remember specifically where you parse the values in each record. There are two ways of doing that. One is to use a special delimiter, like a $sign. Suppose $sign is never used by any of your records in any of its values. I can use the $sign to indicate the boundary between values in a record. Then you just keep going until you hit the delimiter. You know that's the end of the current value, beginning of the next value. Or alternatively, you can use a kind of like a directory entry at the beginning of the record and use pointer to point to the boundary of those values. Both approaches are fine. The benefit of second approach is that it allows you to do random access to any values in a record. But the downside is that the overhead is a little bit more compared to the first approach, because each $sign, each delimiter occupies just 1 byte. Whereas once you start remembering the offset values, it's an integer. Even though, of course, these are not typical integers, these are small integers because you are remembering the offset values of the record. And at its maximum, probably some value of tens or hundreds. So using 2 bytes probably more than enough. But still, you're using 2 bytes per boundary position. Right? So it's a little bit more overhead. Any questions on this? Now, finally, we're ready to discuss the organization of records. Now, for fixed length record, this is needed. I can, partition a page into what we call multiple slots, where each slot is exactly your record size, because the record is fixed length. Now, given any record, if it's fixed length, I can actually go into any of slots on your page, because each slot is exactly the record size. And all records having the same size, so it doesn't matter where they go. So there are two organizations. One is I push all the records together continuously, and that's what we call record space. And the remaining slots that's not occupied are called free space. And I simply use n, this value n, to denote the number of records I have. Effectively, this value n denotes the boundary between free space and record space. So that's one approach. The downside of this approach is that if you delete a record, you have to compact the record space because you are making records continuously to each other. Right? So you have to do the compact operation, which can be expensive. But the benefit of this approach is also very obvious, which is the free space are consecutive, so that insertion is very easy. You just keep inserting to the first slot available from the free space. You don't keep track where I should place the record to. The second approach says, I don't want to do that compact operation every time after a deletion. What I will do is, I will ask record to go anywhere on my page, any slot. So the white and black slots are interleaving in this case. In this case, you do need to remember for a given slot whether it represents a record or just some random bytes, some junk. In order to do that, what I use is what we call a bitmap at the bottom of your page. The bitmap has basically two parts. One is the value m, which indicates the total number of slots I have on this page, and a size m-bit bitmap. And each bitmap has a bitmap means it's a collection of bits, and each position is either 1 or 0. 1 indicates the corresponding slot has a record. 0 means the corresponding slot does not have a value, does not have a record. There is a delicate relationship between the page size, record size, R, and value of M. They have to satisfy certain relationship. What is that relationship? Which is?
R plus m can't be greater than p.
Say again?
R plus m cannot be greater than
R
p.
plus M. It's actually more tricky than that. M is the number of slots you can have on this page, right? What's that relationship? Let's assume I use 4 bytes to represent the value of M itself. So this is the integer that occupies, let's say, 4 bytes. And typically, it doesn't require 4 bytes because the number of slots in a page is probably 2 bytes is more than enough. 2 bytes is what? 2 bytes is already 2 to the power 16, right? That's a large number, right? Each byte is 8 bits. So 2 bytes is enough, right? Let's assume we're using 2 bytes for this. So P has to minus that 2 bytes to use for that, to allocate the space to remember this value M. And I also have to minus the space required for that bitmap, which is M bits. Convert that to bytes, that's M divided by 8 bytes. The remaining space is used for what? To store records. And each record occupies R bytes. That's how many records I can hold for this page. Of course, this may not be a perfect integer. I have to take the floor of that, not the ceiling of that, because the remaining number of bytes is not enough to hold a record. So those become wasted. And this whole thing equals to exactly what? This equal to what? Can someone tell me? This equals the number of records you can hold in this page, which is M. You solve this equation, you get the value of M.
What's m over 8?
Number of bytes for this bitmap. Because you have M bits. Okay, so that's the relationship here. Now, that's fixed length record. Variable length record is much more involved. I don't have time to discuss that. I will use the remaining 1 or 2 minutes to demonstrate something related to your project, which is, when I go into a database, I somehow magically know what are my table names? What are the indexes I have? Which are views, which are tables? And what is the schema of each table, and so on and so forth. Somebody has to store this information somewhere. And how do database systems do that? And you know what? The database system takes a very simple solution. Database is designed to store tables. But typically, people would think about table as user data. But in fact, database systems use table also for system data. That's what we call catalog. I'm going to show you using the Postgre database that we have. So if you do this, this will show the list of tables from the current database you are connecting with. If you use, but in fact, what this does is showing actually this. Public, in PostgreSQL, they define something called namespace. It's kind of like namespace in your C++ or packages in your Java. What's viewable under a package. So by default, whatever under public is viewable to you, and by default, DT stands for describe table, meaning show all the tables from this public domain. So that shows all the tables from this database DVD rental. You can also do D+, followed by, for example, a table name. That will describe the schema information of this table. Schema information of this, and how this table was built with indexes and even triggers. Okay? And where all this information are stored? Well, they are stored in something called PG catalog. So all this information are stored in tables themselves, in special tables of themselves. Example, PG class is a table store all the table names from your database. So if anyone create a table in your database, that will create a new record in the PG class table from the catalog space. That makes sense? Let me demonstrate that for you. Example, if I execute this, statement, okay? What I got is the relation name and object ID currently in my database. Example, actor is the relation name with the object ID assigned to it in this table. That's how the database know, oh, there is an actor table. And what you may wonder, okay, now I know there's an actor table. What about the attributes in the actor table? Well, you can do that. You can let's execute another example. Let's assume I'm doing this. So what this does is to select the object ID, attribute name, and attribute type, and attribute length from the catalog attribute table and catalog class table, where the attribute relation, I join that on the object ID and relation name equal to payment. What I'm saying is, show me the attributes and their types and their lengths for all attributes in the payment table. So I got payment ID, customer ID, and so on and so forth. Of course, there are some other attributes that is actually not viewable to you if you just describe the payment table. Let me run this again. So if you show the payment table, it only shows this attribute. But if you run that SQL query above, it shows additional attributes, because some attributes are system attributes that are hidden from the end users. But if you know PG well enough, you can find out all the secrets they hide from you. And of course, you have to be admin to do this. But I think using our class account user ID, you can execute those SQL queries I show in my slides and to play with PG catalog to understand what's going on. That being said, final word. In your project 1, in your lab 1, you are required to implement schema and so on and so forth, right? The implementation of that. And that's essentially what's going on here. Essentially, you are treating them as nothing else but just tables in your underlying system. All right. With that, I will come back on Thursday to talk about variable length records, and we're done with the storage manager, buffer manager, and all that. I will move on to something else. Okay. But you have everything you need to know for lab 1 by now.